Okay, so good afternoon, everyone. Happy Friday. It's a pleasure for me to introduce our speaker today. It's Dr. Seyed Mansouri. He is an associate professor in the Department of Chemical and Biochemical Engineering at Technical University of Denmark. Seyed received a PhD from the same institution a few years ago, and I would like to say that I first met Seyed when he was one of the most active organizers of one of the freshly conference in the broader processes engineering community. So Seyed's research focuses on the broader area of systems engineering. That includes process system engineering, system dynamics, educational technologies, socio-economic technological analysis, as well as process design, control, and intensification for various chemical and biochemical manufacturing systems. So he has been very active in multiple professional organizations and has received quite a few awards. So now, floor is yours, Seyed, please.
Thank you very much, Fenchi, for the nice introduction and having me here as a part of this series at Cornell's Systems Engineering. So my name is Seyed Mansouri. I come from the Technical University of Denmark. So DTU's mission is to develop and create value through technical and natural sciences for the benefit of society, and it was founded by Hans Christian Ørsted, the founder of electromagnetism around 200 years ago. So we celebrated DTU's 200-year anniversary a while ago, and it has also gone through several evolutions during its time. It was founded in 1929, and basically has been merged several times with several national labs within Denmark. And today, DTU is built upon this motto of technology for people. So this is our ambition to bring our research to education, innovation, and public-private scientific advice. So DTU has several locations. Its main campus is on the northern outskirts of Copenhagen in the city of Lyngby, with several other campuses across the country, and also some research facility in Greenland. So where do I come from? I come from this tiny country in the Northern Europe, in Scandinavia, Denmark. DTU is located, as I mentioned, on the northern outskirts of Copenhagen, in a city called Lyngby, and this is our little mermaid in Denmark, which we are very proud of. And this is Nyhavn, one of the picturesque locations in Copenhagen, and this is DTU's central administration building. So with this little introduction about my institution, I begin my talk for today on process systems engineering at the interface of innovation, education, and policy. So what is the motivation and challenge? So today we are facing several challenges, as most of us know, with resource scarcity. We are striving to find more efficient processes, better use of raw materials, reducing waste, improving the economics of the processing systems, less consumption of energy and water, and so on. So the fundamental question is how these improvements can be attained. And one of the ways that we can achieve these objectives and tackle the grand challenges of our today's society is to generate innovative solutions and to achieve more sustainable designs. So one way and one discipline that can largely contribute to this endeavor is process systems engineering. So process systems engineering is an interdisciplinary field within chemical engineering, and its objective is to develop systematic procedures using mathematical models and computational techniques for the analysis, design operation control, and optimization of process systems at various scales. So process systems engineering was also founded by Professor Roger Sargent back in 60s, and this is a quote I found from Professor Sargent, where he says process systems engineering is all about the development of systematic techniques for process modeling, design, control, etc. So over the years, process systems engineering has found its application in various domains, including modeling, process synthesis and design and analysis, product design, tools integration, and sustainability, as I mentioned, at various levels of aggregation within the process and systems. And it has today become a field of interest to many researchers around the globe. So what is needed from process systems engineering? So in a nutshell, I'm just going to present this, and that is we need databases for compounds, properties, experimental data. We need model libraries, we need methods, we need computer-aided tools for each one of these stages in process systems engineering, which in each one of these main steps in process systems engineering that where it is very dominant. First being synthesis, where the objective is to find the optimal process routes, and design and analysis, where we actually look into the process designs and try to identify their bottlenecks. And then one way to tackle their bottlenecks to turn them into more sustainable and profitable production systems is process intensification. And eventually we need to come up with the strategies on how we can control and operate these processes. So what we need in process systems engineering is an integrated framework that can encompass different levels of aggregation, different levels of complexity, and the size of problems, so we can all the way start from a mean and arrive into an end. So often this problem is formulated mathematically in form of a given objective function subject to a set of constraints, and for each type of these problems, of course, there is a given set of information, and the objective is to find an optimum solution for that objective. So this was an introduction to from my side to process systems engineering. So to my talk, I will actually follow is this multi-layered view of chemical and biochemical engineering, which I participated in its development as an activity of European Federation of Chemical Engineering a couple of years ago. So as you can see, there is the core fundamental layer of the chemical engineering. There is the middle interface layer where science and engineering need to come together and work hand in hand to provide innovative solutions and arrive into more sustainable alternatives for existing process systems. And then we have this outer unifying layer where all these activities need to come for the benefit of the society in form of education and tackling the grand challenges and opportunities of our today's society, and finding the application of these solutions in industrial development. So I will start from the inner core fundamental, where the processes and products are. Examples from our own research, and I will continue layer by layer. So the inner core fundamental layer is to achieve the knowledge that is required in the core of the chemical engineering, such as chemical kinetics, transport phenomena, unit operations, process integration, and so on. So process systems have a multi-scale nature, and the fundamental understanding is at the heart of being able to find the interconnectivity between each one of these scales. Sometimes the pain, and maybe that is in most cases, sometimes the pain is felt in the process systems at a given scale, while the root cause is located in another scale. So understanding a multi-scale understanding of the process systems from a fundamental point of view is important. So for this, we need knowledge of unit operations, transport phenomena, reaction engineering, separation and technologies, and so on. And that we call it the core chemical engineering. So within the core chemical engineering, what we are currently doing in our research, the first example is this modeling stone wool dissolution. That is a project in collaboration with the Rockwool company. And the goal is to provide the company with a model that is able to predict the dissolution rate to reduce health impacts in human lungs. So as you can see here, we are using the molecular dynamics at the quantum scale to solve the problem. And this is a problem that we can tackle it, better understanding and find a solution if we look at it at a very small scale. However, the end impact of the solution will be on the final product that will be used in the society. Another example here is where we look into the process intensification and when it comes to sustainability. So a lot of times when we are talking about the hazards, we are traditionally the objective is to look at the hazards or the hazardous compounds that are produced during processes as something that we have to spend money to mitigate them. One of them being a hydrogen sulfide. It is a gas or molecule that is quite abundant and harmful in the oil and gas production, and it also incurs a lot of costs on this industry and environmental challenges of the chemicals that are being used to mitigate this. So here we have started looking at it from another angle, saying that what if this is still a raw material? Can we find a solution that we can generate revenue and convert it to a more sustainable product that can also have an application? So here is where we have been looking at doing a multi-scale optimization, starting from doing the quantum chemical calculations at the molecular level, identifying reaction barriers and reaction pathways, using different green solvents. And what we have arrived in is actually an intensified unit operation in form of a biphasic reactor where there is an organic solvent phase and an aqueous and an H2S rich aqueous solution, where we are converting H2S to benzyl mercaptan in a sustainable way, which is actually a product that has quite many applications in the society, in the chemical industry, and is a building block in many different polymers, for example, insulating material and so on. So what we have done here is that in this single unit operation, we have a combined reaction, two-phase mixing, phase contact, and phase transfer phenomena into a single unit operation to show that process intensification and not only can solve a lot of sustainability challenges, but it can also open doors for us to be able to look into some problems from a different angle. Another example at the core chemical engineering are these fish diagrams. So these diagrams are actually phase diagrams that are in shape of a fish. This is the fish. So traditionally, calculating these fish diagrams is quite resource intensive and is expensive. So what we are doing is that we are at a molecular scale looking at how we can actually generate these fish diagrams. And these diagrams are very important to efficiently design emulsions for product formulation, especially in pharmaceutical industry. A lot of a lot of pharmacists or formulators in pharmaceutical industry rely on know-how information and rely on a recipe-driven approach to design these formulations for emulsions, whereas with such tools that are generated computationally at a lower level aggregation, molecular level, and with molecular level understanding, we can potentially save enormous amounts of time for formulation experiments. So what we are doing here is that we are actually combining machine learning with an image-based continuous image analysis to combine it with these first principle models to develop an integrated causal effect tool for designing emulsions, which can potentially have a lot of impact within the formulation industry. In a while, I'm going to show this hybrid approach and how we are using machine learning and these core fundamentals in our approach in a moment. Another application is the micellar catalysis, again at the core chemical engineering fundamental layer. And so so a lot of organics they are using organic solvents, whereas given the properties of the micelles in water, they're water soluble, they're green. However, there are a lot of challenges in using them to catalyze organic synthesis reactions. So what we are also looking here is can we actually design tailor-made these micelles first computationally, and then we synthesize them in the lab. So this is again can drive a major sustainability problem in the pharmaceutical industry towards a more sustainable solution. So these are a few examples at the core chemical engineering layer. Now I will give some examples now how we try to combine these core fundamentals within the middle interface layer, where science and engineering are coming together. So innovative solutions for service provisions need to be determined at this middle interface layer, and this requires additional knowledge in terms of integration of science and engineering, leading to development of innovative solution and approaches to process integration and intensification. So one of those approaches is data science and machine learning now. So here is actually something that perhaps many of you in the audience are familiar with, but I will reiterate on, and that is on one doesn't necessarily need to use a very complex machine learning and AI algorithms for many problems in chemical engineering. So other simpler and more transparent artificial intelligence techniques are often adequate. Then the question is that, okay, then within this paradigm of artificial intelligence, where can we use artificial intelligence for chemical engineering problems? And the question is that how can we leverage the great amount of prior knowledge that we have within the core layer, fundamental layer of the chemical engineering. So in my opinion, using artificial intelligence does not mean that we have to forget what we already know and what we have already understood from the nature. Instead, we need to figure out the ways that we can complement what we cannot understand with basically the data and combining them with the prior knowledge. So here I'm quoting Venkata Subramanian at Columbia University. He's also within the field of process systems engineering. So that mechanism-based causal explanations are at the foundations of science and engineering. So the way that, and I agree with him, and the way that we want to use machine learning in our approaches is to develop mechanism-based causal explanations. So in this essence, we are now developing hybrid machine learning modeling frameworks. Now I show examples from our own research on particle processes. So what we are doing here is that we basically have the first principle model. In this case, the first principle model is the population balance model that we embedded within the hidden layers of deep learning artificial neural network. So what it does is that the first principle model will, in principle, give the machine learning model some constraints that to avoid some overfeeding or underfeeding features that are quite common with machine learning approaches. So as you can see, it is a layer by layer structure, and the first principle model is embedded within the hidden layers of the deep learning neural networks. So here is what we're talking about. If in many cases that we are dealing with processes that they have strong foundations in laws of nature, physics, chemistry, and biology, using at least our observation in many industries is that using pure machine learning approaches often results in a risk of overfeeding or underfeeding, whereas when we go to a hybrid approach, we can fortify this risk by using the first principle models, and those first principle models are actually the prior knowledge that we have generated in our disciplines. So the way that we have implemented our approach is that at the moment we are using the TensorFlow framework provided by Google, and this will, in a moment, I will show that how we then incorporate this kind of hybrid modeling with data acquisition methods. So the first example is the hybrid machine learning modeling of particle processes. This case was a full-scale industrial antibiotic crystallization for a major Danish company. As you can see here, the batches had very different properties. They also had very different conditions during the batch operation. So what we did here, we have used a non-invasive measurement technology that is capable of providing online particle size distribution, and also image analysis using the segmentation algorithms. And we combined this data and pushed them through this hybrid machine learning framework. And what we could see is that given the uncertainty that was available within different batches, different operating conditions, and so on, the model could substantially outperform pure machine learning based approach and provide the predictions in a satisfactory way. So in another example, we are looking at process called flocculation. So flocculation or agglomeration is actually a major primary purification process in many biomanufacturing processes, where by adding a polymer to the fermentation broth, we can actually remove the cell debris, organic biomass, and so on. So these particles will coagulate with each other, and they will form so-called brain flux. However, quite surprisingly, there is no control monitoring system available today for these processes in the industry. So often the control is like this. So it is taste-based. So operators, they take a sample, they measure the turbidity or just look at it, and then they say if it is good or not. But what happens in reality in biomanufacturing is that a lot of expensive pharmaceuticals or bio-based specialty products are actually lost in the flux because of the lack of control on their breakage or agglomeration. So what we have done in this case is that we started actually modeling the breakage term in the population balance model, and the breakage phenomena of in particle processes with density functional theory, understanding the first principles at the core fundamental layer, and then we embed that within the hidden layers of artificial neural network, because again, with image processing, with a non-invasive measurement technology, we managed to monitor and to monitor the growth and the dynamics of this process over time, and we generated data, and we have shown that it is actually possible to monitor and eventually control these processes with these hybrid approaches. So that has brought us into developing the Delphi Twin platform. So Delphi Twin is an integrated digital twin for bioprocess monitoring and control. So this is the reactor where fermentation or crystallization or flocculation could happen. This is the non-invasive measurement technology, and this is where the model, the hybrid model, is updated real time, and then it is passed on to a model predictive controller, and then we have closed the loop, and this system is actually now working in closed loop. So this, we call it a breakthrough in terms of developing digital twins. We have so far, we have other applications also on chromatography and CHO cell fermentation, and several other applications of crystallization. And we have seen that this approach has turned out to be quite powerful. We also need to note that this hybrid framework is actually independent of sensor signals, so we can actually push multiple sensor signals into the framework as well. So with that, I come now to the outer unifying layer, which is to improve the social benefits. So as you know, today in many countries, we are talking about achieving the UN Sustainable Development Goals. We are thinking of strategies, how we can achieve these goals, and so on. So to this kind of endeavor requires integration of chemical and biochemical engineering know-how together with other disciplines, for example, sociology, ethics, political sciences, and economics. That is why systems engineering and particularly process systems engineering is a very interdisciplinary, versatile discipline within chemical engineering. So again, I quote John Prosnitz. So perhaps many chemical engineers have heard the name of Professor Prosnitz for his groundbreaking works in molecular thermodynamics. He has emphasized this aspect together with the special role of the human dimension in chemical and biochemical engineering. So this human dimension is also now something that we are trying to consider in our research group structure and our research activities. So this brings me to circular economy and resource recovery. So we have many processes, almost all processes. They use raw material, they produce the products, they generate waste, and now what will happen to the waste? So do we need new technologies, policies, or a combination of both to close the cycle? But here is something that circular economy, from a monetary point of view, can be actually circular. But from a physical point of view, I mean, given the second law of thermodynamics, I mean, the entropy of the systems are increasing. So in order to, so the processes are not reversible. So when it comes to circular economy, from a physical point of view, it's not completely circular. So I often prefer calling it a circular helix. So that it is propagating now, at what rate it propagates, then it is our responsibility as human beings. And so the time dimension also in circular economy from the process systems point of view is also something important. So that is where obtaining more optimal processing pathways that generate less waste and less energy and so on is very important. I know that Professor Fenchi Yu has a lot of groundbreaking work in this area, but I am also showing one example from our research. So biosuccinic acid is identified actually as one of the 12 most important chemical building blocks, the succinic acid. However, I mean, succinic acid today is produced from petrochemical resources, whereas it's been a few years, maybe more than 2 decades actually, that biosuccinic acid had become attractive as a bio-based commodity product. However, one thing that we realized was that the 4 commercially available biosuccinic acid plants have either gone bankrupt in the past few years due to the oil price fluctuations, or they are struggling economically. One of the examples is the BioAmber company that went bankrupt. So we started through a superstructure optimization activity, think of what were the root causes of this bankruptcy. And so it's quite interesting that all the technologies that we included in the superstructure are TRL7 above. So meaning that more or less they're all available off the shelf, including the fermentations. However, when we did the superstructure optimization, we realized that actually none of the commercial processes were in the top 1/3 of the solutions in our optimization. So we started thinking, okay, then we need to further analyze these processes. So we included first generation, second generation, and third generation feedstock. And one thing that we have arrived at, the results, I think within the next few weeks, will become available in energy and environmental science. And what we arrived in is that actually there is a trade-off between the type of the technology, the feedstock, and the number of plants that are built from a given feedstock. Of course, there's also an important factor here to also include the policies, how the banks have been giving loans, the payback times, and also so how the governments are providing subsidies to bio-based manufacturing processes, especially for commodity chemicals. So another aspect is also CO2 and thinking of carbon neutral biorefinery concept. So in this case, we actually combined the top solution for biosuccinic acid production from our superstructure optimization, that it uses glycerol and CO2 as the feedstock, and we combined it with biodiesel production because glycerol is a rather problematic byproduct of biodiesel production, because finding buyers for it is often difficult at the locations that the biodiesel is produced. And then we also looked into the methanol production from CO2 under the circumstances that we are capturing the CO2 from this plant, or we have built this plant close to, let's say, a cement factory, for example, that produces a lot of CO2. So what we arrived in is that the fully integrated solution is not necessarily the most economic and sustainable solution if you combine all three. So if you combine all three, that means that we are only feeding carbon dioxide and waste cooking oil in this process. And then everything else is actually integrated. All the wastes are going into product. And then we have two product streams of biodiesel and succinic acid. But actually the optimal solution, the more feasible solution, is where succinic acid is only combined with the biodiesel production process. This is just an example that we try to look into how integrated our processes should be. And then if we fully integrate the processes towards zero waste production, then what could be the challenges? What could go wrong? Which is currently subject to our ongoing research. Finally, we look at between the layers, artificial intelligence, quantum computing, and education. And the question is that why? Why should we look at these interactions? First of all, we want to look into the education because of various reasons, because of the increase of the population, safety, introduction of technologies, the new habits, educational needs, and allowing mistakes. And perhaps most of us have by now realized that distance learning and the efficacy of learning from distance needs to be more and more put into the perspective of academia if you want to actually have engineers who can have hands-on experience, especially during these difficult times of COVID-19 pandemic. So having that said, we started thinking of hypothesizing on an educational simulator, and simulators are commonly used for education in chemical engineering and also in other disciplines of chemical engineering. Here I'm naming a few well-known process simulators used in chemical engineering education and as well as research. However, none of them have an embedded learning design coming with them. So that means that they are not, philosophically, they're not designed for education. They're designed for somebody who has been educated to better use them. Of course, we use them in our classrooms, but they are not autonomous as such that somebody can see and can learn and master a subject within the education, let's say process design. Aspen or ISIS could be very useful tools to solve the problems. They're very good calculators, but they're not necessarily on their own suitable for education. And so therefore, the need that we found was a simulator that not only has the knowledge, but also can explain and motivate the users while they fail and repeat. So this is where we started building upon the learning through failure, or facilitating learning through failure within the simulation environment. However, the failure may turn into becoming something frustrating, so we have to make it also enjoyable. So this is where we have developed the methodology and the software, a prototype software that basically we are combining systems engineering principle in terms of developing a systematic framework, as well as model reuse, construction and implementation through template-based modeling, providing process description, and eventually putting a top layer on this whole thing using game-based learning elements or gamification elements to develop a pedagogical the features of a high-level process simulator, but at the same time, people would like to stay inside this simulation environment and learn and repeat and fail. And so we have shown the application of this platform. It's called BioVL now. We have shown its application on several examples. For the interest of time, I have skipped showing the demos, but if anybody is interested, you can contact me and then we can provide a demo. So once we have designed the process, we're required to design and do the implementation of such framework. So the framework is within 3 layers of presentation layer, application layer, and data to access layer. And one thing that I want to mention is that, for example, the Delphi Twin platform that we have developed also has all these layers. So let's say once we have a fully validated digital twin of a process, that digital twin can go into the BioVL platform as something for education. And since it is a digital twin of a real process, then it can be used, and we can hope through careful pedagogical and learning design that we can also create intuition for the engineers, for the future engineers, and also for more complex, complicated processes that may be very costly to train engineers at universities and as well as companies. So this is also an overview of data access layer that is embedded within this platform, and the application layer where we are using the template concepts that we develop generic modeling templates that also in future, when people are developing new models, one problem that is in many research groups often and in industries, that a lot of times when people develop their models, the next person coming on board has to re-implement that model. So having a sort of a generic template for modeling that you can store, reuse, and recycle the models is quite attractive. Now this brings me to computational agility in systems engineering, artificial intelligence and quantum computing. Again, and Feng Chi is also having a fruitful program here at Cornell on quantum computing, which also excited us to also get into this area, and we are finding more and more excitement. And this, if you look into the evolution of technology and the computers, I mean, and this is how us human beings have evolved from learning point of view. So if the technology is evolving at a fast pace, we also need to evolve from learning point of view and provide means for current and future generations to learn about these technologies, so that we can have the required highly specialized workforce to use and leverage these technological advancements in future. So quantum computing and artificial intelligence are two of the areas that perhaps there is a need to develop careful education and pedagogical elements to bring them into the curriculum. This is a survey that we have recently done around the current status of quantum computing and chemical engineering. And since 1960s, little over 100 publications within this area are related to chemical and biochemical engineering applications, let alone a few applications only on industrial cases. So there's a lot of space for chemical engineers to explore this computational agility within the chemical and biochemical engineering discipline. And in principle, process systems engineering discipline uses the computational tools, and we feel that within this community we are positioned correctly to tackle this area and explore the opportunities for these applications. So the question is, how can chemical and biochemical engineering benefit from this agility? We have to solve more problems, to collaborate, we have to discuss, and then we need to have this community to come together and discuss what could be these benefits. Also, we have looked into hybrid quantum computing algorithms. Again, FNG has done a lot of work in this area. What we did in this work was that we just made some evaluations on the effectiveness of hybrid quantum algorithms on current hardware, quantum hardware that is available. And well, the conclusion is that for some problems, depending on the type of optimization algorithm that you choose, there is plenty of work to do. Sometimes the classic computer may outbid the quantum computer, but the point is that once the capacity of quantum computers increases, hopefully we can expect that quantum computers can solve larger problems, larger discrete problems much faster. And to this end, we have together with AICHE, we are organizing the Quantum Computing Applications Workshop in Chemical and Biochemical Engineering, which again, we have the pleasure of having FNG as one of our featured speakers in this event. So what brings me to the end of my talk is that now the next step is that we want to look into Calimbo symbiosis. So Calimbo symbiosis is one of the world's most comprehensive industrial symbiosis that is available. So it is 100 kilometers away from Copenhagen. There is port, there is refinery, there is renewable energy, wind and solar. There is biomanufacturing, wastewater treatment, many pharmaceutical industries, utility facilities, and so on. And what is happening in Calimbo is that in Denmark, since the vision is to become carbon neutral by 2050, we are looking at Calimbo actually as a very good example that we can use, that we can do as a test bed for a lot of integration. Also, it creates a lot of opportunities to deal with the the public-private stakeholder and technological advancement of the and how the policy and innovation. There are many also startup hubs in this area. So this is where we are thinking ahead, larger, more complex, more dimensions of complexity, which we hope that in future we can also collaborate with Cornell systems engineering in this area. So as you can see, this is, for example, Kalambo utility. This and the heat integration that has been done in Kalambo. So actually today they have nearly completed full integration of mass material and energy flows between these different sectors and large industries in Kalambo, and have shown that substantial reductions can happen. So this is actually a very good example of a lot of things that we are in systems engineering, process systems engineering for many years. We are talking about, we are showing evidence. Here is one of the examples that it is to some extent implemented, but there are plenty of rooms for more implementation. And the examples of logical growth as a result of this sort of systems thinking and integration towards sustainability is that there has been over 2.3 billion USD investment in this symbiosis over the past few years, and more than 2,000 jobs are created, and the production has increased to an extent that the harbor had to be expanded quite substantially. And finally, our department with the industries in Kalambo has and the help and support of the Novo Nordisk Foundation, we have created the Biotech Manufacturing Project House, where it is supposed to be a hub for students to do industrial bachelor's, master's, and PhD project in very, very close vicinity of the production. So the students, so their housing places, virtual reality facilities. So we are aiming at developing many digital twins of the unit operations in this process, in large industries for training and education, and also pilot scale facilities. So to bring academic research and the stakeholder interests for more agile labor in future, and the large industries in one place. So today we have the possibility to look into larger, more complex process systems. There's a need to develop education at the same time as we develop the technology, and new modes of education need to be developed to meet demands of the industries of future. So with this, I would like to thank you for paying attention to my talk, and I'd be happy to take questions.
Thank you so much, Seyed. Very nice talk, very comprehensive, introduction about all activities that are being involved. So now I think the floor is open for questions. Any questions from the audience?
So I have one question regarding your idea of a helix rather than a circular economy. I really like that. Now, energy-wise, if you put in energy, you won't have any.
I'm sorry, Al. I'm not hearing you clearly.
Okay, I know what happened. I'm sorry. I had put down my. Is this better?
Now it's better.
Okay, I'm sorry. I took off my headset while I was listening. And anyhow, so your circular diagram for sustainability, I really liked your idea of making it into a helix. Now, from an energy point of view, if you have energy input, it doesn't have to be a helix. But I was particularly struck with the idea of the physics, and I'm not sure I understood exactly what you meant, but I'd like your comments on the energy aspects of it, and also the physical dispersion of materials through waste. In principle, I suppose, with enough energy, you wouldn't have to have that happen. But the way we operate almost everything in the world, we disperse concentrations of things, oil, whatever, and disperse it into the environment in such a way that it's a sort of physical entropy, right? And I just wonder if you have any comments on that, because I like that idea.
Well, I think you pointed out rightly. If we have access to, let's say, enough renewable energy, I mean, a lot of these problems that do not exist. But in the situation that we are far from having access to that amount of renewable energy, to spend the energy to reverse these processes and then these dispersed concentrations that you're mentioning, then we still have a challenge. Now here is the question of time. I always use this example of the gene. I always use this genes example. So, there is this guy, when you use your genes, for example, I mean, after a while you throw them out, right? So there was this guy in London, his name is Tariq Mohammed. So he has started making very fancy carpets from used jeans. So now the question is that, okay, after 50, 60 years or 100 years, then what is going to happen to the fancy carpet? We may burn it or landfill it or whatever, and then it is going to be ashes. So there is the time domain. So the question is that eventually a lot of these material may go back to their initial state, but that will be beyond our life span. So I think the question is quite philosophical in a way. So if I want to be even more open about it, I would say the problem can be solved much easier from a consumer point of view than from a technological point of view.
Yeah, that's true. I think it's a philosophical problem, and it's a long time scale, but it's on the same kind of time scale of climate change and general habitability of the planet. I mean, not that 100 years is that far away from the point of view. I have grandchildren, and they'll have children eventually, and I think we do have to think this way. But I think your helix is a nice way of thinking about it. I like that a lot, and I like some of your ideas about education as well. Thank you for the talk.
Thank you very much.
I think it's Anna just raised the hand, right? Yeah, Anna, please. Can you unmute yourself?
Yeah. Thank you. I really enjoy the talk. Thank you, Seyed. I have a question regarding the Kalumbor project or system. I really like it. I'm fascinated with that. Really, really fascinated. And I was also fascinated about the ideas you talk about, the educational models, the simulations with the design and everything. But the one that I want to ask you about this project house that it's going to be working, I understood that it's going to be in the area of Kuala Lumpur, or whatever called in Danish. Can you tell us about that? Is it already working? How is it going to start this project? I really, really like this idea of the companies and the house and the students.
I think it's also very nice. I think it's also a very nice idea. So I'm actually going to an information meeting next week to also figure out more details on how this will be implemented on the ground. But from the ideas that have been out there to go for it, is that to create the workforce that already is gaining hands-on experience on site. So not having students who are educated in the best case in a lab, or if in some universities the resources allow in a pilot scale facility, and then expecting them to be able to convince a company to give them a job while they have never seen a real plant. So this the idea is partly because many students, when they go for a job market, they're often asked for at least a couple of years of industrial experience. So it's actually a paradox that cannot be solved for many many students. So so this could actually resolve that problem in a way if large industries start collaborating with universities in a symbiotic way to create this intuition. I mean, I'm talking about creating virtual labs and so on, but if students can be very close to the industry to gain that intuition while they are students, then they will be fit to get a job immediately after graduation.
Yes. Thank you. Thank you. I think we will discuss it further when we meet each other.
Great. Well, thank you so much. Any other question? Any last minute question? We are running out of time, so just to make sure we get a chance to give the floor to anyone that want to ask. Otherwise, thank you so much. You can say this is wonderful talk. Really appreciate it. In the normal time, we'd like to have you here, show you around the campus, and then at this moment, we should give you a gift back. But because of the virtual format, I cannot give you the gift back right now. But I did reach out to our event coordinator, Daniel. He's going to send it to you by mail so that you can receive the gift back.
You can send me the pictures, so that can work.
We will send you the file as well. Well, it will be mailed to you to Denmark.
Thank you very much. Thank you.
All right. Okay, thank you so much, Seyed, for the time.
All right.
And to everyone.
Thank you very much. Thank you very much for the invitation. Bye.
Bye-bye.